This video was brought to you by Squarespace. Squarespace. Square your space. My name is Dylan Wu, and we are going to talk about Dirty Cow. In this video, we are going to try and answer a couple of questions about the exploit. First, what is the exploit and how do we use it? I'm actually going to do a demo on an unpatched version of Ubuntu 16.04 to show you guys what the exploit looks like on an actual Linux machine. Next, we're going to go into detail about race conditions, how they work, and the specific implementation of copy on write that triggers it. Afterwards, we look at the actual code of the exploit and use the knowledge that we've gathered from the demo and the explanations to interpret the code. So what is Dirty Cow? Cow is an exploit that affects Linux kernel versions 2.6.22 to 2.6.39, and it is an exploit that actually remained unpatched for around 9 years. The vulnerability was discovered a while back, but was unpatched because patching it actually introduced another bug, and at the time, laptops weren't fast enough to make use of the vulnerability, but as time went on, things changed, and it became a really serious threat. The technique is used for privilege escalation, meaning it tries to promote your user permissions to that of root, but it can also be integrated with other exploits to remotely execute non-privileged code as root user. And the way it's implemented is by exploiting a race condition. A race condition is basically when the kernel tries to run two or more processes simultaneously using shared data, and the proper execution of both processes depends on the timing and sequence of program execution. Okay, so now I'm going to show you guys what the exploit looks like. So as you can see, I currently do not have root permissions, and if I try to access the root directory, my permission is denied. So let's see what happens when I run the cow root exploit. So as you can see, I was able to get root access to this machine, and if I cd into root now, I can, and I can get the flag. You can see that my user ID is now root. So that's basically what the privilege escalation process looks like. Okay, so now I'm going to give you guys a concrete example of what a race condition is. So let's say you have a bank and it has $100 and you make a request for $100. So what happens in this situation is that after you make the request, the bank tells the server that you requested $100, the server sends back a message, changes the $100 to 0, and you get $100. Well, what happens if you send out a request to the bank, and then immediately after you send out the first one, you send out a second request? Well, if you are lucky, then the bank sends out the request to the server to update the information, and before the information can be sent back from the server, you have made your second request, and the bank is none the wiser. So you have now got yourself $200. And in this situation, the race is basically between the second request and the response from the server. And if the second request is sent out first before the server response is sent to the bank account, then you get $200. Okay, so now we are going to talk about copy on write, or COW. So copy on write is actually a very simple idea. So let's say you have two processes, P1 and P2, and they both have their own respective virtual memory spaces. And you have some physical address space over here. And if P2 and P1 are both using the same code base, what happens is that the kernel allocates one chunk of physical space for both of the two code bases because they're using the same code. So there's no reason for the kernel to, use up more space than it needs to. So it has both of the code bases in the virtual memory spaces from P1 and P2 mapped to the same address space in the physical memory space. But let's say that P2 suddenly decides that it needs to make some changes to this code. Well, it can't make changes to the original physical space because if it does that, then P1 will get affected and it won't be using with what it thinks it'll be using. So what the kernel does is it says, okay, you want to make some changes? Let's make some changes. So it allocates a new chunk of memory in the physical address space by making a copy of the original code base. And so now P2 can make any edits it wants to this copy. And whatever changes that it makes to the copy will not affect the original kind of code base. So P2 can now make edits or do whatever it wants here, and it won't have any impact on P1's processes. And that is copy on write. Okay, so now we're going to integrate cows and races. So you have your physical address space here, and you have two processes, process 1 and process 2. And in your physical space, you have some memory allocated for file A, which only the root user has access to. So that means you cannot make any changes to A. If you want to make changes, then you have to create a copy of A called B. You can do whatever you want in B. And this is exactly what P1 does. It makes a copy of A called B, and then it writes to B. And process 2's job is even simpler. Its only job is to set the pointer back to A. So when it's done writing, it basically deletes B and then resets the memory location pointer back to A so that process 1 can run again. So in a non-exploitable world, what this looks like is P1 runs, P2 runs, and then you go back to P1. But in the exploitable world, what can happen is that both process 1 and process 2 can run a million times. And so at some point, what will happen is P1 gets executed and you have A to B. But then, instead of writing to B, process 2 also gets executed and you go back to A from B. And then remember, process 1 never finished. So that means you can now write to A. And this is the race that occurs. You are racing process 1 and process 2. And if process 2 at any point happens to get ahead of A, then you can now write into memory location A with root permissions. Okay, so now we're going to talk about the exploit that I used to get root permissions in my virtual machine. I'm not going to go through the exploit line by line just because of time constraints, but I will attach links in the description for anyone who's interested in the explicit system calls that are used, as well as the different variations of Dirty Cow that have been written by different people. These individuals include Live Overflow, who's a hacker that does popular videos on different popular exploits, and this professor called Kevin Du, who did a really good lecture on privilege escalation, race conditions, and Dirty Cow. And so just to really briefly go over what the code in the exploit is doing here, the first thing to notice is that you are putting the usermid password file into SUID binary, and you also have your shellcode here. And this is the shellcode that you're actually going to be replacing user bin password with. And we'll see how that works in the main method. Okay, so here you can see that we're first creating a backup of user bin password in case you need to restore that file somehow. And you are crafting your payload here. As you can see, you have your NOP sled, you have the shellcode, and then here is the mapping statement where you are placing into physical memory you're basically mapping into physical memory user bin password so that you can replace it when you run these 3 threads. You'll notice that it's 3 threads instead of the 2 that we talked about, and we'll see what's going on there. So the 2 threads that are related to the ones we talked about in the previous slide, so are these 2. So you have the madvise thread and you have the procself_mem thread. The madvise thread is basically the P2 process that we talked about before, and the procself_mem thread is basically the P1 process. You can see that both are running about 1 million times, and here in the procself_mem thread, you are actually reading in user bin password, and this is where the copy on write is happening. So you basically copy into a new location, then you write to that new location, and then here you are mapping back to your original location. And so once these 2 threads are running simultaneously, if the madvise thread ever happens to get ahead of procself_mem thread, then you have the race condition being successfully executed, and you are able to write into user bin password. And then you have the final thread. This thread is actually really simple, so it just lets you know when user bin password has been overwritten, and then it executes user bin password, which has been replaced with the shellcode. So when you run suid binary, it's calling whatever's in user bin password, but you have replaced user bin password with your shellcode. So you're actually calling your shellcode, which is how you're getting your shell with root permissions. Finally, some key takeaways from this video. I hope you guys learned about what Dirty Cow is, what race conditions are, what copy on write is, and how they work together to form the Dirty Cow exploit. And finally, I hope you guys learned about how the code of Dirty Cow actually works. So it basically creates 2 threads that race against each other, and when they're successful, when the code is successful, it spawns a shell with root permissions. Last but not least, a shout out to our sponsors at Amazon Prime. Amazon Prime, join us before it becomes obligatory.